Early September 1943, Kursk salient, Soviet Union. The captured Panther Aus-D rolled through the gates of the Kubinka proving grounds, 60 kilometers west of Moscow. Its mottled camouflage paint still bore the tactical markings of the 3rd SS Panzer Division Totenkopf. Soviet engineers and military observers gathered around this prize, notebooks already open, cameras ready. This single German tank, captured intact during the desperate fighting at Kursk 2 months earlier, would trigger a crisis of confidence among Soviet tank designers that would echo through their armoured vehicle programs for years. The revolution in tank warfare was about to be revealed, not through thicker armour or more powerful guns, but through something Soviet industry had never mastered, vertical precision that transformed gunnery from approximation into science. The Panther bore chassis number 210.51, built at the Mann factory in Nuremberg in May 1943. It had been abandoned by its crew near Ponary Station on July 10th, 1943, after a mechanical breakdown during the German withdrawal. Soviet recovery teams from the 41st Guards Tank Brigade towed the immobilized vehicle kilometers to a collection point, then transported it by rail to Moscow. Every detail would be documented, measured, and analyzed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Soviet tankers who had fought Panthers at Kursk watched the arrival at Kubinka with mixed emotions. They had experienced firsthand what this machine could do. Panthers had engaged T-34s from distances where Soviet tanks could barely identify targets. German gunners achieved first-round hits at ranges exceeding 500 meters. Soviet crews firing back watched their shells fall short or bounce harmlessly off sloped frontal armor. The mathematics of the engagement had been brutally one-sided. The Red Army had paid a terribly price learning about the Panther. During Operation Citadel, Sherman forces deployed approximately 200 Panthers, most allocated to the 48th and 39th Panzer Corps, attacking the northern face of the Kursk salient. These new tanks were supposed to restore German offensive capability, breaking through Soviet defensive lines that had defeated previous attacks. Instead, the Panthers suffered catastrophic mechanical failures that eliminated more vehicles than Soviet fire. But when they worked, when the engines ran and the transmissions held, Panthers demonstrated gunnery capabilities that shocked Soviet observers. Soviet after-action reports from Kursk documented the disparity in engagement ranges. T-34 crews reported that they could not effectively engage Panthers beyond 800 meters. The T-34's 76mm F-34 gun simply lacked the accuracy at longer distances. Soviet gunners could see Hermann tanks in the distance, but hitting them reliably required closing to ranges where the Panther's superior gun could destroy Soviet tanks with impunity. German gunners, by contrast, engaged confidently at 500 meters and beyond, achieving kill rates that seemed impossible to Soviet tactical doctrine. At Kubinka, the testing facility that served as the Soviet Union's primary center for evaluating both domestic and captured foreign military equipment, engineers prepared comprehensive examination protocols. They would measure every dimension, test every system, and compare the Panther against Soviet designs across dozens of parameters. The facility, established in 1931, had evaluated captured German equipment since the opening days of Operation Barbarossa. But nothing examined previously matched the Panther's combination of firepower, protection, and the optical sophistication they were about to discover. The initial inspection began with teams of specialists from multiple technical branches. Armor metallurgists examined the steel composition and welding techniques. Powertrain engineers evaluated the engine and transmission. Weapons specialists studied the 75mm Quake 42 gun and its mounting, but it was the optical specialists who made the discovery that would dominate Soviet technical discussions for months. The Panther mounted a TCF-12 monocular telescopic gun sight, manufactured by Zeiss, the German optical firm, whose product set global standards for precision. Soviet engineers had heard reports about German optical superiority, but seeing the device firsthand revealed capabilities that Soviet industry simply could not match. The sight provided 10 times magnification with exceptional clarity across the entire field of view. The reticle pattern, etched onto glass with micrometer precision, allowed range estimation and lead calculation with accuracy. Soviet gun sights could not approach. Senior Lieutenant Mikhail Baryatinsky, an optical engineer assigned to the Kubinka evaluation team, would later write in technical reports about his first examination of the TZF-12. He described removing the sight from its mount, carefully examining the lens assemblies, and understanding immediately that Soviet optical manufacturing could not produce equivalent devices. The glass quality, the coating technology preventing reflection and glare, the mechanical precision of the adjustment mechanisms, all exceeded Soviet capabilities by margins measured in years of development. The TZF-12 incorporated multiple innovations that Soviet gun sights lacked. Multi-layer anti-reflection coatings on all glass surfaces reduced light loss and improved image brightness, particularly in low-light conditions at dawn and dusk, when much armored combat occurred. The reticle pattern included range marks calibrated specifically for the Panther's 75mm gun, allowing gunners to estimate target distance and adjust aim accordingly without complex mental calculations. The sight body was sealed against moisture and shock-mounted to maintain zero even after the violent recoil of repeated firing. Soviet tank gun sights, by comparison, used simpler optical designs with fewer lens elements, resulting in reduced magnification and image quality. The standard PT-47 telescopic sight mounted in T-34 tanks provided only 2.5 times magnification. This meant Soviet gunners saw targets at less than 1/4 the detail German gunners observed. At 1,000 meters, a German gunner could identify vehicle types, distinguish between variants, and aim at specific weak points. A Soviet gunner at the same range saw indistinct shapes requiring closing distance before confident engagement. The testing program at Kubinka included comparative gunnery trials designed to measure actual combat effectiveness under controlled conditions. Engineers set up target arrays at measured distances from 500 meters to those 000 meters. They included stationary targets, moving targets, and partially concealed targets simulating battlefield conditions. Both captured Panthers and standard Soviet tanks would fire at these targets, with accuracy, time to first hit, and hit probability all carefully recorded. The results were devastating to Soviet confidence. Firing from static positions at known ranges, German optical equipment allowed Panther gunners to achieve first-round hit, probabilities exceeding 80% at 1,000 meters against tank-sized targets. Soviet T-34 crews using standard PT-47 sights achieved approximately 45% first-round hit probability at the same range. This disparity meant German tanks could engage with confidence at ranges where Soviet tanks were reduced to area fire, hoping for lucky hits. Moving target engagements demonstrated even wider capability gaps. The Panther's gun mount included a hydraulic turret traversy system powered by the main engine, allowing smooth rotation that kept the gun sight picture stable during aiming. The gunner could track moving targets continuously, maintaining the crosshairs on the target while calculating lead and range. Soviet T-34s used manual turret traverse, requiring the gunner to physically rotate the turret using hand wheels. Tracking a moving target while simultaneously operating traverse controls and preparing to fire required exceptional skill and coordination most gunners never mastered. Additionally, the Panther mounted a gun stabilization system, though crude by later standards, that reduced vertical gun movement during vehicle motion. This allowed Panthers to fire while moving with reasonable accuracy, a capability Soviet tanks completely lacked. Soviet doctrine assumed tanks would stop, aim, fire, then move, because hitting targets while the tank was in motion was nearly impossible with unstabilized guns and basic optical sights. German tanks could engage while maneuvering, maintaining offensive momentum while delivering accurate fire. Soviet engineers documented these differences in exhaustive technical reports that circulated through military and industrial hierarchies. The optical disparity was not merely inconvenient or a minor disadvantage. It was fundamental, determining who saw whom first, who engaged at longer range, and who achieved killing hits before the opponent could respond effectively. All the armor protection and firepower in the world meant nothing if you could not see your target clearly enough to hit it. The Zeiss TZF was not the only optical advantage the Panther possessed. The tank commander's cupola mounted 7 periscopic vision devices providing all-around visibility without exposing the commander to enemy fire. These periscopes used the same high-quality optics as the gun sight, giving commanders exceptional situational awareness. The commander could scan the battlefield, identify threats, and direct the gunner onto targets rapidly and efficiently. Soviet tank commanders typically had fewer and lower-quality vision devices. The T-34 commander's cupola included basic periscopes with limited fields of view and optical quality barely adequate for general observation. Identifying specific threats, particularly at longer ranges, required opening the hatch and physically looking outside, exposing the commander to small arms fire, artillery fragments, and enemy observation. Many Soviet tank commanders were killed or wounded while attempting to observe from exposed positions because their vision devices were inadequate for combat conditions. The Germans also equipped the Panther loader and driver with periscopic vision devices of good optical quality. The driver had 3 periscopes providing forward and limited side visibility. The loader had a single periscope allowing observation on his side of the turret. Every crew member could contribute to situational awareness, spotting threats and targets that might be outside the commander's or gunner's immediate field of view. Soviet tanks provided minimal vision devices for positions other than commander and gunner, reducing crew effectiveness and limiting tactical awareness. Beyond the immediate optical advantages, Soviet engineers examining the Panther discovered German attention to details that Soviet tank design had never considered priorities. The gun sight included an illuminated reticle for night firing, powered by a small battery and allowing engagement in darkness when Soviet tanks were effectively blind. The commander's cupola could rotate independently of the turret, letting the commander maintain all-around observation, while the gunner engaged targets in a different direction. The turret included internal lighting adequate for crew operations in all conditions, while Soviet tanks often operated in near darkness inside the fighting compartment. These features seemed like luxuries to Soviet designers, accustomed to producing tanks under desperate wartime conditions with limited resources and industrial capacity. A tank crew that could see clearly, identify targets at maximum weapon range, and engage effectively in varied conditions, was worth far more than raw numbers of vehicles with inadequate sighting equipment and vision devices. The Kubinka testing included evaluation of the Panther's range-finding capabilities using the graduated reticle pattern in the TZF-12 sight. German gunners were trained in a systematic method for estimating target range based on the apparent size of enemy vehicles viewed through the sight. The reticle included horizontal hash marks of known angular width. By noting which hash mark corresponded to the target's apparent width, the gunner could calculate range using simple memorized tables. This range-finding method, while not as precise as dedicated optical and range finders used on some German heavy tanks, provided sufficient accuracy for first-round hits at combat ranges. More importantly, it was fast, requiring only seconds for a trained gunner to estimate range and adjust aim. Soviet gunners lacked comparably tools. They relied on experience and judgment to estimate range, methods that worked adequately for experienced crews but left novice gunners floundering during their critical early battles. The German training system emphasized gunnery skills far more extensively than Soviet training programs. German tank gunners received weeks of instruction in range estimation, lead calculation, and engagement techniques before joining combat units. They practiced on simulators that replicated actual combat conditions. They fired hundreds of practice rounds on gunnery ranges, developing muscle memory and refining techniques until achieving hits became almost automatic. Soviet tank training, compressed by wartime urgency and limited ammunition. Availability provided far less preparation. New crews received basic instruction in operating their tanks and firing the main gun, then were sent to combat units where they learned through experience if they survived long enough. This disparity in training quality compounded the equipment disadvantage, creating situations where poorly trained Soviet gunners using inferior optical equipment faced highly trained German gunners equipped with superior sighting devices. The reports from Kubinka made uncomfortably reading for Soviet military leaders and industrial administrators. The technical gap was undeniably and could not be closed quickly. Developing optical manufacturing capabilities matching German standards required years of industrial investment, skilled worker training, and technology development. The Soviet optical industry, focused primarily on producing adequate quantities of basic equipment for the massive Red Army, lacked the precision manufacturing capability and quality and control standards necessary for devices like the TZF-12. Soviet attempts to copy captured German optical equipment revealed the depth of their industrial disadvantage. Engineers disassembled TZF-12 sites, carefully measuring every component and documenting the assembly process. They created detailed technical drawings specifying dimensions, materials, and tolerances. Soviet optical factories attempted to manufacture copies using these specifications. The results were disappointing. Soviet-produced copies achieved perhaps 70% of the original performance, suffering from reduced image clarity, less precise retically etching, and mechanical adjustments that did not hold zero reliably. The problem was not lack of knowledge or understanding. Soviet engineers comprehended the principles of advanced optical design as well as their German counterparts. The limitation was industrial capability. German optical factories employed workers trained through multi-year apprenticeships in precision manufacturing techniques. Quality control inspectors rejected components that deviated from specifications by micrometers. Assembly technicians adjusted and aligned lens elements with tools and techniques developed over decades of producing high-end cameras, microscopes, and surveying equipment for global markets. Soviet industry, by comparison, emphasized production quantity over quality refinement. Factories operated under pressure to deliver equipment rapidly in massive quantities to equip millions of soldiers fighting desperate defensive battles. Quality control standards were relaxed to maintain production rates. Worker training emphasized speed and volume rather than precision craftsmanship. These systemic differences, rooted in decades of different industrial development paths, could not be overcome through simple reverse engineering or copying captured equipment. By late 1943, Soviet tank production had recovered from the catastrophic losses of 1941 and 1942, with factories producing over 34 tanks per month. This quantitative advantage allowed the Red Army to replace losses and maintain numerical superiority over German armored forces. But Soviet commanders understood that quantity alone was insufficient against German tanks, whose optical advantages allowed them to engage first and hit reliably at ranges where Soviet return fire was largely ineffective. The optical disparity influenced Soviet tactical doctrine significantly. Red Army tank units began emphasizing close-range engagements where Soviet numerical superiority could overwhelm German technical advantages. Soviet commanders learned to use terrain, concealment, and aggressive maneuver to close engagement ranges rapidly, accepting heavy casualties during the approach, but achieving favorable exchange ratios once at close quarters, where Soviet guns could penetrate German armor, and Soviet numbers could surround individual German tanks. This tactical adaptation, while pragmatic given equipment limitations, resulted in casualty rates that would have been unacceptable to Western armies. Soviet tank units routinely suffered 40 to 60% casualties in major offensive operations, losses that were replaced from the seemingly inexhaustible production of Soviet factories. German units, despite their optical and gunnery advantages, could not sustain similar loss rates because their tank production never matched Soviet output. The Panther evaluation at Kubinka continued through autumn 1943 and into early 1944 as additional captured vehicles arrived. By February 1944, Soviet forces had recovered approximately a dozen Panthers in various conditions from battlefields across the front. Several were restored to running condition and tested extensively. Engineers evaluated automotive reliability, armor effectiveness, and firepower, but the optical systems remained the aspect that most impressed and frustrated Soviet technical evaluators. Soviet industry responded to the optical challenge through multiple parallel approaches. Designers worked on improved gun sights, incorporating some features observed in German equipment while remaining within Soviet manufacturing capabilities. The TZF-15 sight, developed in 1944 for the upgunned T-34-85, provided 4 times magnification, double the previous standard, but still far less than the Panther's 10 times magnification. The improvement was significant but inadequate to close the capability gap. Engineers also developed the TZF-16 sight with 5 times magnification for heavy tank programs, moving closer to German standards. Production examples appeared in late 1944, equipping IS-2 heavy tanks and some T-34-85s. These sights represented genuine progress, incorporating better optical quality and more sophisticated reticle patterns, but they still did not match the clarity, brightness, and overall effectiveness of German Zeiss equipment. The fundamental limitation remained industrial capacity to produce high-quality optical glass and precisely manufacture complex lens assemblies. Soviet glass manufacturing struggled with consistency, producing batches where individual elements varied in optical properties, enough to degrade overall performance. German optical glass from manufacturers like Schott maintained tight specifications across production runs, ensuring consistent performance. This difference, invisible in specifications but critical in actual use, separated adequate equipment from excellent equipment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Additional captured Panthers arrived throughout 1944 as Soviet offensives pushed German forces westward. By year's end, Kubinka had evaluated over 20 Panthers of various production types, documenting the evolution of German tank design and identifying running changes introduced during production. Later Panthers incorporated improvements addressing reliability problems that had plagued early vehicles, but the optical equipment remained consistently superior to Soviet equivalents across all production variants. Engineers noted with particular interest that German optical quality remained high, even as Germany's war situation deteriorated. While late-war German tanks showed evidence of material shortages and production shortcuts in many areas, the gun sights maintained their precision and effectiveness. This reflected German priorities, understanding that crew effectiveness depended critically on vision and sighting equipment. Compromising optical quality would reduce combat effectiveness more than using slightly thinner armor plate or accepting less powerful engines. Soviet technical intelligence also acquired information about German training methods through interrogation of captured tank crews. Prisoners described gunnery training programs emphasizing rapid range estimation and first-round hits. They explained the systematic approach to engaging multiple targets, prioritizing threats based on distance and capability. They demonstrated the methods used for engaging moving targets, including lead calculation techniques and tracking procedures. This information, combined with understanding the superior equipment German gunners possessed, explained much about German gunnery effectiveness in combat. Soviet training programs began incorporating some of these German methods, teaching systematic range estimation and improved engagement techniques. But without equivalent optical equipment, Soviet gunners remained disadvantaged regardless of training quality. A mediocre gunner with excellent equipment could outperform an excellent gunner with inadequate equipment, particularly at longer engagement ranges where small differences in sight picture quality translated into large differences in hit probability. By spring 1945, as Soviet forces approached Berlin, captured equipment included late production Panthers with night fighting equipment, demonstrating continued German emphasis on optical superiority. Infrared searchlights and receiving sights allowed Panthers to detect and engage targets in complete darkness, capabilities Soviet tanks lacked entirely. These systems were rare, fitted only to small numbers of vehicles, but they represented the technological trajectory German designers pursued despite their nation's deteriorating strategic situation. The final major evaluation at Kubinka involved comparative gunnery tests between captured Panthers and the newest Soviet designs entering service. The T-44 medium tank, developed as the T-34's successor, incorporated lessons learned from German designs, including improved armor layout and better automotive components. But its gun sight remained inferior to German equipment, using the TS-15 with 4 times magnification. Similarly, the IS-2 heavy tank, mounting a powerful 122mm gun, capable of destroying any German tank, relied on sights that could not exploit the weapon's full potential at maximum effective range. Engineers calculated that IS-2 crews could theoretically engage targets at dose 500 meters with their powerful gun, but the sight's limited magnification and optical quality made accurate fire beyond 500 meters unlikely. This meant the IS-2's gunnery performance, despite superior firepower on paper, was constrained by optical limitations to ranges only marginally greater than the T-34 it was meant to surpass. The Panther's inferior 70-mm gun, coupled with superior optics, achieved comparably or better practical effectiveness through consistent accuracy at longer ranges. These findings, documented in detailed reports from Kubinka and distributed through Soviet military and industrial channels, influenced post-war Soviet tank development significantly. When Soviet designers began work on the T-54 medium tank in the immediate post-war period, they emphasized improving sighting equipment and vision devices. The T-54 incorporated better gun sights with improved magnification and optical quality, commander's cupola with better all-around vision, and generally improved crew optics across all positions. The lesson learned from evaluating captured Panthers was clear. Technological superiority in firepower and protection meant little without the optical equipment to employ them effectively. A tank's combat power was not determined solely by the thickness of its armor or the caliber of its gun, but by the crew's ability to detect threats, identify targets, estimate range accurately, and achieve first-round hits reliably. German optical superiority had multiplied the effectiveness of their tanks beyond what specifications suggested, allowing German crews to dominate engagements against numerically superior Soviet forces. Soviet industry never completely closed the optical quality gap during World War II. German equipment remained superior in most respects through the war's end. But understanding the disparity and its tactical implications allowed Soviet commanders to develop doctrines that minimized German advantages while maximizing Soviet numerical superiority. The Red Army won through overwhelming force, accepting casualties that would have been unsustainable for Germany, producing tanks faster than Germany could destroy them, and slowly, but inevitably, grinding down German resistance. The captured Panthers at Kubinka also revealed broader lessons about industrial warfare and the relationship between technological sophistication and practical battlefield effectiveness. German tanks like the Panther represented the apex of precision engineering applied to military equipment. Every component was manufactured to exacting standards. Every system was designed for optimal performance, but this pursuit of technical excellence came at enormous cost in production time, specialized materials, and skilled labor. Soviet tanks, by contrast, embodied pragmatic simplicity. The T-34 was designed from the beginning for mass production by semi-skilled workers using available materials and standard industrial processes. Its systems were deliberately simplified to reduce manufacturing complexity and maintenance requirements. This approach sacrificed some performance, particularly in areas like optical quality and crew comfort, but enabled production rates that ultimately proved decisive. The optical disparity exemplified this fundamental difference in design philosophy. German designers specified Zeiss optics because they wanted the best possible sighting equipment, understanding that superior optics multiplied crew effectiveness. Soviet designers specified adequate optics that Soviet industry could produce reliably in massive quantities, accepting reduced individual tank effectiveness in exchange for numerical superiority. Both approaches had logical foundations based on their respective nations' industrial capabilities and strategic situations. Germany, with limited industrial capacity and access to resources constrained by Allied blockades and strategic bombing, needed individual tank superiority to offset Soviet numerical advantages. Each German tank had to be more effective than its Soviet counterpart because Germany could never match Soviet production numbers. Superior optics helped achieve this effectiveness multiplier, allowing German crews to engage earlier and hit more reliably. The strategy worked tactically, with German tanks consistently achieving favorable kill ratios in most engagements. But favorable kill ratios proved insufficient when the enemy could replace losses 10 times faster than you could. Soviet production of T-34s exceeded 25,000 vehicles during the war. German Panther production reached approximately 6,000 vehicles, less than one-fifth Soviet output. Even if Panthers achieved 5-to-1 kill ratios, the mathematics still favored the Soviets over time. Soviet commanders could accept heavy losses in individual battles, knowing replacements were continuously flowing from factories beyond German reach. The testing at Kubinka documented another critical observation about optical equipment performance under actual combat conditions. German sights were precision instruments requiring careful maintenance and protection from shock and contamination. The TZF-12 performed brilliantly when properly maintained in good condition, but combat exposed these delicate instruments to violence that degraded performance. Heavy recoil from firing, rough terrain vibration, battle damage from near misses, and simple environmental exposure all affected optical alignment and clarity. Soviet maintenance practices, adequate for robust, simple equipment, often proved inadequate for sophisticated German devices. Captured Panthers, operated by Soviet units, frequently experienced optical problems as seals degraded, allowing moisture infiltration that fogged lenses. Shock from combat knocked optical elements out of alignment, producing double images or blurred sight pictures. Soviet field maintenance personnel lacked the specialized tools and training to repair these problems, rendering the superior equipment less effective than it should have been. This raised uncomfortable questions for Soviet designers, considering whether to pursue German-style sophistication. Even if Soviet industry could manufacture equipment matching German optical quality, could Soviet maintenance systems keep it functioning under combat conditions? Would precision equipment survive harsh treatment by conscript soldiers with minimal training and rough field and conditions across thousands of kilometers of front? Soviet designers concluded that robustness and simplicity offered significant advantages for equipment serving in the Red Army's operational environment. The Germans themselves struggled with maintaining their sophisticated equipment under deteriorating conditions from mid-1944 onward. As fuel shortages worsened and spare parts became scarce, even simpler maintenance often became impossible. Panthers with optical damage sat disabled, not because the sights could not be repaired, but because no replacement parts were available. Factory production focused on complete new tanks rather than spare components, leaving field units unable to maintain existing equipment. Precision devices requiring specialized maintenance became liabilities rather than assets when maintenance systems collapsed. Soviet observers noted this phenomenon with interest. Reports from frontline intelligence officers documented increasing numbers of Zeiss German tanks abandoned with relatively minor damage that could not be repaired. Panthers immobilized by thrown tracks sat beside roads because recovery vehicles lacked fuel. Tanks with damaged optics were abandoned because no replacement sites existed. The German maintenance system, adequate for a victorious army operating from permanent bases with short supply lines, failed catastrophically when forced to sustain operations across vast distances with interdicted logistics. By comparison, Soviet maintenance practices, though crude, proved remarkably resilient. T-34 crews performed field repairs using improvised tools and scavenged materials. Damaged vision devices were replaced with battlefield expedients, sometimes simply removing damaged periscopes and looking through the open hole. Engines were swapped from destroyed tanks in hours using basic tools and manual labor. The T-34's simple construction and Soviet crews' pragmatic approach to maintenance kept operational readiness rates relatively high despite heavy combat losses. These observations influenced post-war Soviet military thinking about equipment design. Simplicity, robustness, and maintainability became explicit requirements weighted alongside pure performance specifications. Equipment had to function reliably in hands of conscript soldiers with minimal training operating under field conditions that routinely destroyed delicate precision devices. Soviet designers understood from examining German equipment that sophistication and effectiveness were not synonymous under real combat conditions. The captured Panthers also provided opportunities to evaluate German crew ergonomics and fighting compartment design. Soviet engineers noted with interest that German tanks provided substantially better crew working conditions than Soviet equivalents. The Panther's fighting compartment offered generous space, allowing crew members to move and work without constant interference. Seats were properly designed and adjustable. Controls were logically positioned within easy reach. Ammunition stowage was organized for efficient loading. Every detail reflected attention to crew effectiveness and combat efficiency. Soviet tanks, designed to minimal dimensions to reduce target size and manufacturing cost, cramped their crews into confined spaces where simply performing basic tasks required constant physical effort. T-34 crew members worked in positions that would be considered intolerable in Western armies. The loader had to wrestle heavy ammunition rounds from awkward floor stowage while bracing himself during vehicle movement. The gunner operated controls positioned for mechanical convenience rather than ergonomic efficiency. The commander had to simultaneously observe the battlefield, command the crew, and assist with loading during sustained combat. German designers understood that crew fatigue degraded combat effectiveness. Well-rested crews in comfortably working conditions fought more effectively than exhausted crews struggling with poor ergonomics. The Panther's spacious interior allowed crews to maintain effectiveness during extended combat operations. Soviet crews in cramped T-34s tired rapidly, reducing their already disadvantaged gunnery performance further. This represented another multiplier effect, where German design attention to crew factors enhanced overall combat capability beyond what equipment specifications alone suggested. However, Soviet designers consciously accepted reduced crew comfort as a trade-off for other advantages. The T-34's compact dimensions provided a smaller target profile and lower weight that enabled better mobility. Reduced interior volume meant less armor plate required, allowing thicker protection for given weight or lighter overall weight for given protection. Soviet doctrine emphasized that tanks would primarily be crewed by young soldiers who could physically tolerate harsh conditions, and that combat operations would be relatively brief before casualties forced crew replacement. This revealed fundamentally different assumptions about armored warfare. German doctrine assumed relatively stable crew assignments, where experienced veterans remained with their vehicles across multiple engagements, accumulating experience and achieving high effectiveness. Soviet doctrine assumed high crew casualties requiring continuous replacement with minimally trained personnel. German doctrine optimized for sustained effectiveness by experienced specialists. Soviet doctrine optimized for acceptably effectiveness by inexperienced replacements operating simply equipment. The optical disparity fit within these broader doctrinal frameworks. German emphases on long-range precision gunnery reflected their defensive strategic situation from mid-1943 onward. German tanks fought primarily from prepared positions, engaging Soviet offensives at maximum range, where their optical advantages were most decisive. German commanders understood they lacked numbers to trade losses equally with Soviet forces. They had to achieve favorably exchange ratios through superior gunnery, destroying multiple Soviet tanks for each German loss. Soviet doctrine, by contrast, emphasized offensive action with tanks operating as exploitation forces, penetrating deep into German rear areas. This role required reliability, mechanical simplicity, and adequate rather than optimal gunnery. Soviet tanks needed to reach their objectives despite opposition, mechanical stress, and logistical challenges. Once in the German rear, even mediocre gunnery could destroy supply columns, headquarters units, and artillery positions that Soviet doctrine identified as primary targets for tank exploitation forces. These different operational concepts explained why the optical disparity, though technically significant, proved less decisive strategically than it might have been. German tanks used their superior optics to achieve impressive defensive successes, destroying Soviet tank units in grinding attritional battles. But these tactical victories did not translate into strategic success because Germany lacked the production capacity to replace losses and maintain force strength. Soviet offensives absorbed heavy casualties but continued advancing as fresh units, replaced damaged formations faster than Germany could contain them. The interrogation of captured German tank crews provided additional insights into how optical advantages translated into combat effectiveness. Experienced German gunners described their systematic approach to engagements. They scanned systematically using the commander's superior optics to detect targets at maximum range. They used the excellent gun sight to identify target types, distinguishing between T-34s, heavy tanks, and tank destroyers, prioritizing the most dangerous threats. They estimated range using the reticle pattern, selected appropriate ammunition, and achieved first-round hits at ranges where Soviet return fire was ineffective. This methodical approach, enabled by superior optical equipment, allowed German crews to dominate individual engagements against multiple opponents. One Panther, properly positioned with good fields of fire, could engage and destroy several Soviet tanks before they closed to effective range. Soviet tankers described the terrifying experience of watching their vehicles explode from unseen German tanks, firing from positions they could not identify. The combination of German optical superiority and tactical skill created psychological effects beyond pure combat results. But captured German crews also acknowledged that their advantages were increasingly meaningless by late 1944. Soviet artillery had achieved crushing superiority, delivering preparatory bombardments that destroyed German positions before tanks ever engaged. Soviet air power, negligibly in early war, 2 years, had grown into a formidable force, providing close air support that German fighters could no longer contest. Soviet numerical superiority had reached levels where even favorable kill ratios were insufficient, with multiple Soviet tank armies attacking simultaneously across frontages too wide for German forces to defend adequately. German gunners admitted in interrogations that perfect optics and excellent gunnery could not compensate for being overwhelmed by sheer numbers. When 20 Soviet tanks attacked a position held by 3 German tanks, superior optics allowed those 3 tanks to destroy perhaps 10 or 12 attackers before being overwhelmed. But the remaining Soviet tanks accomplished their mission, and German losses could not be replaced, while Soviet casualties were made good within days. The optical advantage, though real and significant, was ultimately insufficient to overcome the broader strategic disparity. The Kubinka testing program expanded to include evaluation of German training materials captured alongside tanks. Technical manuals, gunnery training guides, and range estimation tables provided insights into how German crews were prepared to exploit their superior equipment. Soviet translators worked through these documents, extracting relevant information for incorporation into Red Army training programs. The materials revealed sophisticated methods for range estimation, target identification, and engagement techniques that Soviet training had never systematically addressed. Soviet gunnery training had traditionally emphasized simple rules of thumb and intuitive methods suitable for minimally educated recruits. German training materials assumed literate, technically competent crew members who could understand and apply systematic procedures. The German approach required more training time and produced fewer qualified crews per year, but those crews achieved substantially higher effectiveness. Soviet approach produced larger numbers of adequately trained crews rapidly, accepting lower individual effectiveness in exchange for numerical advantage. This difference in training philosophy reflected broader social and educational differences between the two nations. German tank crews were drawn from a population with near-universal literacy and often significant technical education. Many German tank crewmen had civilian experience with automobiles, trucks, or machinery that provided foundational mechanical knowledge. Soviet tank crews were drawn from a population where rural peasants with minimal formal education comprised a significant portion. Many Soviet tankers were learning to read while simultaneously learning to operate complex military equipment. The German training materials assumed capabilities that simply did not exist uniformly across the Soviet conscript force. Teaching sophisticated range estimation techniques required numeracy and understanding of basic trigonometry. Training crews to exploit advanced optical equipment required visual acuity and perception that could not be assumed universally. German training could build on these foundations. Soviet training had to begin with more basic fundamentals, accepting that some theoretical capabilities would remain underutilized because the crews lacked prerequisite knowledge to employ them fully. These harsh realities influenced Soviet equipment design throughout the war and into the post-war period. Designers could not specify equipment requiring skills or knowledge the typical crew member would not possess. Controls had to be simple and intuitive. Procedures had to be straightforward, with minimal decision points. Equipment had to tolerate rough handling and continue functioning despite improper maintenance. These requirements constrained design choices in ways German engineers never faced. By spring 1945, as Soviet forces fought through Germany toward Berlin, they encountered the final evolution of German armoured vehicles, including late-model Panthers, with improved optical equipment and night-fighting capabilities. These vehicles represented the culmination of German tank development, incorporating years of combat experience and technological refinement. They were formidable weapons, more capable than the early Panthers tested at Kubinka in 1943. But they were also desperately scarce, with German production collapsed under sustained Allied bombing and chronic material shortages. The Soviets noted the continued emphasis on optical excellence even as other systems degraded. Late-war German tanks showed evidence of material substitutions, simplified manufacturing processes, and quality control compromises forced by desperate circumstances. But the gun sights maintained their precision and effectiveness, reflecting German understanding that optical quality was fundamental to combat capability. This prioritization, maintaining excellence in critical systems while accepting degradation elsewhere, represented sophisticated industrial management under extreme pressure. Soviet industry faced different pressures but made different choices. Soviet production emphasized maintaining output volume while gradually improving quality where possible. New tank variants incorporated better sights and vision devices, but never at the cost of reduced production numbers. Soviet commanders understood that adequate tanks arriving in sufficient numbers were more valuable than excellent tanks arriving in insufficient quantities. The mathematics of industrial warfare drove these decisions relentlessly. The final German defensive battles around Berlin demonstrated both the continued effectiveness and ultimate futility of German optical superiority. Panther crews, fighting from rubble-filled streets with limited fields of fire, achieved remarkably local successes against attacking Soviet armor. Individual tanks destroyed dozens of attackers before being overwhelmed. German gunners exploited their superior optics to achieve first-round hits in chaotic urban combat, where Soviet numerical advantage was constrained by terrain. But these tactical successes could not alter strategic reality. The Red Army simply absorbed the losses and continued attacking with fresh units. German tanks, immobilized by damage or fuel exhaustion, were abandoned when their crews could not retreat. The optical equipment that had provided such decisive advantages in open terrain battles became less relevant in close-quarters urban fighting, where engagements occurred at ranges where even basic Soviet sights were adequate. The war ended with German optical superiority intact but strategically meaningless. The post-war accounting of the Panther evaluation program at Kubinka revealed the scale of Soviet examination efforts. Over 40 captured Panthers had been tested between August 1943 and May 1945. Additional Tiger tanks, Ferdinand tank destroyers, and various other German armoured vehicles had been evaluated concurrently. The testing generated thousands of pages of technical reports, hundreds of photographs and drawings, and extensive comparative data that would influence Soviet tank design for decades. The optical findings received particular attention in post-war analysis. Soviet military theorists understood that their wartime tactical solutions, accepting heavy casualties to close engagement ranges rapidly, would be unacceptably against future opponents who might not be worn down through attrition. Future wars would require Soviet tanks to engage effectively at longer ranges where optical quality determined outcomes. This recognition drove substantial investment in Soviet optical industry during the late 1940s and 1950s. Soviet optical factories received modern equipment and trained workers in advanced techniques. Partnerships with East German optical firms, including portions of the Zeiss works that had fallen within Soviet occupation zones, provided access to German expertise and manufacturing methods. Quality control standards were tightened, and precision manufacturing capabilities gradually improved. By the 1950s, Soviet gun sights approached German wartime standards, though never quite achieving the same excellence in all respects. The T-54 medium tank, entering service in 1946, incorporated substantially improved optical equipment compared to its T-34 predecessor. The T-222 gun sight provided better magnification and image quality. The commander received improved periscopic vision devices providing better all-around observation. Driver and loader positions included better vision devices. The overall improvement in crew optics represented perhaps the most significant capability enhancement the T-54 achieved compared to the T-34, more important in practical terms than its improved armor or more powerful gun. Subsequent Soviet tank designs continued this emphasis on optical quality. The T-55, T-62, and later designs received progressively better sighting equipment and vision devices. Soviet designers had learned from examining German equipment that crew effectiveness depended critically on their ability to see clearly, identify targets rapidly, and engage accurately. This lesson, purchased through examination of captured equipment and paid for with heavy casualties against German optical superiority, shaped Soviet armored vehicle development for generations. The legacy of the Panther evaluation at Kubinka extended beyond immediate technical improvements. Soviet military doctrine evolved to emphasize longer-range gunnery and first-round hit probability. Training programs incorporated more sophisticated range estimation techniques and systematic engagement procedures adapted from captured German materials. Crew selection emphasized visual acuity and technical aptitude more heavily than in wartime, when simply filling positions with available manpower took priority. These changes reflected hard-learned respect for the effectiveness multiplier that superior optics provided. German tanks at Kursk and throughout subsequent campaigns had demonstrated that seeing clearly and shooting accurately mattered more than raw firepower or armor protection specifications suggested. A tank that consistently achieved first-round hits at 500 meters was more combat effective than a tank with a theoretically more powerful gun that rarely hit targets beyond 800 meters. Soviet veterans of the Panther evaluation program, including the optical specialists who first examined the TZF-12 sight in September 1943, carried forward into post-war careers the understanding that technological quality in critical areas could not be compromised for convenience or cost savings. These engineers became influential voices in post-war Soviet military-industrial complex, advocating for investment in optical manufacturing and quality control that would enable Soviet equipment to match Western standards. The investment bore fruit over decades. By the 1970s, Soviet tank optical equipment had achieved parity with Western equivalents in most respects. Laser rangefinders, image intensification night sights, and sophisticated fire control systems gave Soviet tanks capabilities matching or exceeding NATO equipment. The optical inferiority that had plagued Soviet tanks throughout World War II had been eliminated through sustained industrial investment and technology development, but the lesson remained relevant for military establishments worldwide. Technological advantages in critical capabilities could multiply force effectiveness far beyond what simple numerical comparisons suggested. A qualitative edge in sensors, sights, or targeting systems could determine engagement outcomes regardless of other factors. The Germans had proven this at Kursk and throughout their defensive campaigns. The Soviets had learned the lesson through bitter experience and applied it consistently in subsequent decades. The captured Panthers at Kubinka, those silent witnesses to German technical excellence and Soviet industrial pragmatism, served as teaching aids for multiple generations of Soviet tank designers and military theorists. The vehicles remained in the Kubinka collection through the Cold War, available for examination and study. Engineers and officers studied them to understand not just the technical specifications, but the design philosophy behind them. The attention to optical quality, the emphasis on crew effectiveness, the understanding that tanks were weapons systems where every element had to work together harmoniously. Modern military forces worldwide recognize the principles revealed through the Panther evaluation. Sensor quality determines engagement outcomes in contemporary warfare just as optical quality determined engagement. Outcomes in 1943. Thermal imagers, laser rangefinders, digital fire control systems, and advanced targeting pods all serve the same fundamental purpose, allowing friendly forces to detect, identify, and engage threats at maximum effective range before opponents can respond. The technology has evolved dramatically, but the principle remains constant. The story of Soviet engineers examining the Panther's optics and understanding their own deficiency represents a moment of institutional honesty rare in military organizations. Acknowledging weakness, particularly weakness in capabilities claimed as strengths, requires overcoming bureaucratic incentives and institutional pride. The Soviet military-industrial complex could have minimized the findings, argued that Soviet approaches were adequate despite technical inferiority, or simply suppressed unfavorable comparisons. Instead, the findings were documented thoroughly, circulated widely, and used to drive improvements. Senior Soviet military leaders reviewed the Kubinka reports and understood the implications. Industrial administrators received directives to improve optical manufacturing capabilities. Training programs were modified to emphasize the skills that would help crews overcome equipment limitations until better equipment became available. The system worked, slowly and imperfectly, but ultimately effectively. This organizational response to discovering enemy technical superiority offers lessons beyond the specific case of tank optics. Military effectiveness requires honest assessment of capabilities, willingness to acknowledge deficiencies, and systematic efforts to address them. Organizations that cannot admit weakness cannot improve. The Soviets, despite their rigid political system and often dysfunctional bureaucracy, managed to face uncomfortable truths about their equipment limitations and take meaningful steps toward correction. The human cost of the optical disparity can only be estimated, but it was substantial. Soviet tank crews throughout the war engaged German opponents from disadvantageous positions, forced to close ranges where German guns were most lethal because Soviet optics were inadequate for longer-range engagement. Thousands of Soviet tankers died in burning T-34s, destroyed by German tanks they never saw clearly enough to engage effectively. The casualties were accepted as necessary, the price of closing the range where Soviet numbers could overwhelm German quality.